So let's do some entropy calculations. I'm just going to identify these as number 1 and number 2. So let's dive right into number 1. First, we need to identify what equation we need to use. So in this case, it's asking us, a large flask of water is placed in a heater, energy is transferred reversibly, which sounds like it has much disorder, so we're going to have to find our disorder. So our delta S. In this case, it gives me joules and it gives me Celsius. So looking at my equation sheet, I'm going to say, okay, it's probably going to be this equation here. These are the variables that I have, and I'm just going to plug them back in based on this equation, though. So I have 100 joules, and we're always going to use Kelvin. So even though I have 25 degrees C, I'm going to add my 273 so that I can get Kelvin. My answer is going to end up being positive 0.336 joules per Kelvin. So then number 2, calculating my delta S, I have moles, I have a gas, I have an initial volume and a final volume. So based on my equation, I'm going to say, okay, I have my NRLN over V final over V initial, which looks a lot like our ideal gas law. In this case, it's going to be the delta S of our system. So plugging in what I know my 5 moles. I know my gas constant is going to be 8.314 joules per mole times Kelvin. And then my natural log of my 6.0 liters over my 1.0 liters. And the value that I end up getting for my entropy change is 74.5 joules per Kelvin. And we know that these are the same units, so we can compare those values like apples to apples instead of apples to oranges. So in this case, we know a low entropy has little disorder, and a high entropy has lots of disorder. I guess I could also put my little s here so you know. So, but if we think about it conceptually, if you think about adding 100 joules of energy to some water, which is about the same amount of energy needed to power a 10-watt light bulb for 10 seconds. So small little light bulb for 10 seconds. Or if we expand, say this is a balloon or something, if we expand it from a volume of 1 liters to 6 liters, I kind of think of my little balloons. That's a way bigger change than just adding a little bit of heat to some water. So in this case, that makes sense conceptually and mathematically. So we have a higher entropy value here versus here, and that also works in theory. So hopefully this helps you conceptualize entropy just a little bit more, even if my pictures were kind of bad.